I forgot to
Recording.
record. Oh. 361. You guys are going to kill me. Oh, I'm sorry. I'll take a picture of the layers. Maybe that'll help. That's stupid. I just started recording now. But okay, that was dumb. All right. Anyway, let me share my screen. Okay, so we were talking about the delta function potential. And let me just get on this layer again. There we go. And remember, it's kind of a spike that goes down. So it's basically 0 and then straight down, right? Right at 0. So that delta function potential, we said, looks like this up here, this guy here, right? With the minus sign and everything. Okay. And we went through and we solved for the left and the right. And so we got psi left, which was this, and psi right, which was this, okay? And we're now solving here, we're solving for the case 2, right? So this is case 2 that we're solving for, where E total is less than 0, okay? So we're looking for bound states. All right, so we were just showing you an example here of K was 2, right? Or kappa. But we have to have, because of boundary condition 1, we ended up saying that B had to be equal to F. So this B had to be equal to F because right at 0, when I stitch the two pieces together, they have to be the same, right? Because it's continuous. They can't be like jump, right? And so that led us to this solution so far. So this is what we have so far. We have psi is B e to the kappa x for x less than 0 and B e to the minus kappa x for x greater than 0. Notice that they're really dying exponentials on both sides, right? Because if x is less than 0, this is going to be, dying, in other words, e to the negative kappa something, right? And on this side, it's also that way, okay? All right. Okay, so, but we still don't know what B is, right? And we have to implement the other boundary condition, which is boundary condition 2, okay? Let me point out something. So we know what kappa is, but not really, right? So remember what kappa was. So kappa was the square root of minus 2me over h bar squared. So sorry, let me write that differently. There. So it was the square root of minus 2me over h bar, right? So we don't know what E is, okay? So it's kind of like we don't know what kappa is, really. So when we look at this equation here, which tells us what psi is, we don't know what B is, and we don't know what kappa is, okay? So we need to find those, and we only have two things at our disposal, right? One is normalization. At some point, we're going to have to normalize this, and most likely that'll give us our B, my guess, okay? But we're not ready to normalize yet because we don't know what kappa is. So we have another boundary condition here that we could use to get kappa or something. At least we'll get something out of it. Maybe we'll get B, maybe we'll get kappa, but we should probably implement it. So the second boundary condition says that I don't know why that says squared. It shouldn't say squared. It should say just D. Let me fix that for you because it looks bad. So the first derivative of psi has to be continuous everywhere except where V is plus or minus infinity. And we have that case here, right? We have a V that goes all the way down to minus infinity at that point, right? So we expect that the second derivative is going to be nice and continuous, right, on both sides. And then when it hits that 0, it can be discontinuous. It's allowed to be discontinuous, okay? But that makes it really kind of hard to deal with. Like, what are you supposed to do? And here we're going to use a trick that is often used. It's not that often used in sort of undergraduate physics. It's very often used in graduate level physics. And that is integrating over a discontinuity. Integration tends to smooth stuff out. It's kind of like, if you're taking a you think of a really jagged function and you take a running average that's sort of averaging a little window, things get smoothed out. In other words, you're replacing the value with an average over some window, right? Instead of having a bunch of jagged, you just take the average and replace your point and then move the window, and you can kind of smooth things out. So integration kind of is like doing that. It's kind of like summing, right? And it's going to kind of smooth things out a little bit and allow us to deal with this discontinuity, which right now we don't really know what to do with. And so what we're going to do is going to integrate around the 0 point, because that's where the discontinuity happens. Okay. So to do that, we're actually going to integrate the Schrodinger equation and the TISE with the potential in it, because we want to integrate over that 0 point, right? Because that's where the potential is. So over here, when we look at the TISE up here, it doesn't have the potential because we're just on the right or the left, and the potential is 0 there. So, but we're going to do the whole integrate over the whole Schrodinger equation. So what we're going to do is literally just write that down first, okay? So I'm going to write down, I'll do it up here. So we're going to write down, we have minus h bar squared over 2m. And then we have the integral of that first term in the Schrodinger equation, in the TISE. And we're integrating around 0. So here's our 0, right, where the potential is going all the way to infinity. And we're going to go from minus epsilon to plus epsilon. And we're going to take this in the end, we're going to take the limit as epsilon goes to 0. But the integral is going to smooth stuff out for us and make it a little easier. Okay. So we're going from minus epsilon to epsilon. And I just want you to remember that in the end, we're taking a limit, which is going to help us. And then plus, well, actually, let me put in the potential, minus. So we have minus alpha, because alpha is just a constant here, this alpha up here. The integral of the delta function, delta x, times psi dx, right? This is just literally the next term in the TISE, from minus epsilon to epsilon. And then we have, and that's all equal to the integral of e psi, right? So e can come out of the integral as well. Minus epsilon to epsilon of just psi dx. And we're going to look at these in turn. All right, first of all, this one over here, this guy is going to go away when we take the limit, right? Because imagine you're taking the limit as epsilon goes to 0, you're going to have the integral from 0 to 0. So no matter what psi is there, nobody cares, right? Because the integral is going to go to 0. Right, because epsilon goes to 0. So this is going to go away. So we can just ignore him, right? Because as epsilon goes to 0, it's going to be the integral from 0 to 0, right? So gone. All right. And then these two terms we got to do a little more work on. This one is pretty nice because it has a delta function. So remember, delta functions are super, super easy to do integrals of, okay? And so this term is just going to be minus alpha and then psi at x equals 0, right? Yeah, so right, because this guy here, because it's a delta function, just takes this function and puts, you know, wherever the delta function is. In this case, it's at 0, right? Wherever that spike is, it just puts that into psi, and that's it. That's all it does. So that's really easy. So over here we have equals 0. And then on this term, we have to do a little bit more work. So I'm going to actually take this term off by itself. So I'm going to take that term over here, just by itself, and we'll come back. The integral minus epsilon to epsilon and d squared psi dx squared dx. Okay. So we're going to write that again. We have minus h bar squared over 2m. And then we have the integral minus epsilon to epsilon. And then we have, I'm going to write it as ddx of d psi dx. I can certainly do that, right? It's a second derivative, dx. Okay. And then I can use integration by parts. So remember, in quantum mechanics, right, When we integrate by parts, we literally just take the derivative off of, take one derivative off of what it's on and stick it on the other thing in the integral. Now, there's nothing else in the integral except for the, a constant 1, right? Because this is like d squared over here. It's d squared psi dx squared times 1. So I can take that derivative and put it on 1, but the course derivative of 1 is 0. So I don't even get another term. All I get are the boundary terms, right? So in other words, by fundamental theorem of calculus, so I'll write this one more time so maybe it might jog your memory about integration by parts and fundamental theorem. Epsilon to epsilon. And then I'm going to cancel this out, and I just get the total derivative of this thing, right? And of course, by fundamental theorem of calculus, this is minus h bar squared over 2m. And then it's d psi dx at the boundaries, right? That's just fundamental theorem of calculus. And let's figure out what that is. So we have minus h bar squared over 2m. And then I have d psi dx at epsilon minus, d psi dx at minus epsilon. And we can actually figure out what these are because we know what psi is. Here's psi, right? Okay, so I can figure out what this is. So let's come down here and just figure out what is d psi dx at positive epsilon. Well, if positive epsilon means it's over here in the x greater than 0 area. So d psi dx is minus kappa, because I got to take a derivative, b e to the minus kappa x, and then d psi dx at positive epsilon, I'm just going to put an epsilon for x. So minus kappa b e to the minus kappa epsilon. Okay, cool. So now we just got to do the other one. So d psi dx for the when x is less than 0 is equal to kappa b e to the kappa x. And then when we evaluate it at minus epsilon, we get kappa b e to the minus kappa epsilon, because it's minus epsilon I had to put in there, right? Okay, now we can put that in over here. So I'm going to come over here. So this is equal to this stuff here, right, is equal to minus h bar squared over 2m. And then the d psi dx at epsilon is minus kappa b e to the minus kappa epsilon. And then minus this one, so we get another minus sign, minus kappa b e to the minus kappa epsilon. And let's just conglomerate all that stuff. So we get 2 of these terms. So that'll cancel this too. And the minus signs cancel this minus sign. So we get h bar squared over m kappa b e to the minus kappa epsilon. Okay, so now we have to like put that up here, right? Because we just doing a bunch of work down here to get this. So what I'm going to do is I'm going to erase all our work and just put it down here. Okay, so I hope you have it all down. Of course, we are recording. Okay. Okay. All right, I'm going to erase all our work because we don't need it anymore. I'm going to take this and stick it up here just so I don't forget it. So this is h bar squared over m kappa b e to the minus kappa epsilon. That's this term. And then minus this will equal all equal 0. Okay, I'm going to erase this now. Finish erasing. There we go. Okay, now we have all our terms. Okay, and now we can take the limit as epsilon goes to 0. Right? So limit as epsilon goes to 0 here. Well, if epsilon is 0, e to the minus kappa epsilon is just 1. So I end up with h bar squared over m kappa b minus alpha psi 0. I'm just going to call that psi at 0 because it's at x equals 0. Equals 0. Okay, that's cool. So kappa, looks like one more step. Sorry, one more step. Psi at 0, I certainly know what it is, right? It's just b. If you look here, either one of these, it's just b. So I'm gonna rewrite this one more time. I got h bar squared over m kappa b minus alpha b equals 0. That means the b's are gone. So we're not getting b from this. We're gonna get kappa. So this gives me kappa is equal to alpha m over h bar squared. Now, let's see if I actually got that in my notes. That would be nice. Let's see. I could have not gotten that. I gotta check though. Give me a sec. Because I gotta check. M alpha over h bar squared, I got it. Okay, cool. So now we've got kappa. That's great because kappa, it really is E. So I really have E now. Okay, so let's solve for E because that would be nice to have E. So, okay, so from up here, I know that kappa squared, right? So kappa squared is minus 2me over h bar squared, right? And so I can stick in kappa squared here, right? So and solve for E. So kappa squared is, sorry, I should have given myself a little more room, which I did not. So I'm going to erase this. So you can see what kappa squared is here. I'll write it up here. Kappa squared is minus 2me over h bar squared. Okay. Okay, so now I'll square kappa, so we have alpha squared m squared over h bar squared is equal to minus 2me over h bar squared, and the h bars go away, and we get E is equal to minus alpha squared m squared over 2m. So we get rid of one of those m's and finally end up with minus alpha squared m over 2. Okay, let's see if I got that right. That would be nice. Why do I still have an h bar squared? Dude, I think I'm missing an h bar squared somewhere, guys.
Did you not square the h bar squared when you squared k?
You're correct. Thank you. You are correct. This was incorrect. H bar to the 4th. There we go. So it only cancels 2 of them, right? Okay, that's much better. And so this would be on the bottom, right? You agree with that? Yeah? Okay.
Yeah.
So notice that we now have E. I'm going to write it one more time nicely. And it indeed is negative, right? So we have minus m alpha squared over 2h bar squared. Okay, now we have E. So if someone gives you alpha, so you should always assume when you're given like a potential like this that alpha is somehow, any constant they're giving you in there is is something you would be given unless you're specifically asked to solve for it and given other information. Fine, so now we have E, we're good. But we need one more thing, which is B, and that comes from normalizing the wave function. Okay, so we can do that. Let's, I'm gonna erase some of this work, okay? And we're gonna finally get B and we'll have the whole thing. Okay, so we're going to normalize. So we have to normalize. Sorry. Okay, so we have the integral psi star psi from minus infinity to infinity dx, that has to be 1, right? So I'm write the integral over here again. So now we're going to write down, so psi star, right? So we have, we can write psi as like the absolute value if we needed to, right? So if we think about this, what psi look like? Remember, it's a dying exponential over here. It goes up to b, and then it's exactly the same function over here. It's literally like a little mirror image. So you could write, you could be like, oh, you know, psi is e to the kappa times the absolute value of x times b, right? You totally write that. And for this purposes over here, it's a good idea to do that. Just so you can think about it, because you're like, wait, which one of these do I use, right? I don't know. Or you could split your integral into 2 halves, right? Minus infinity to 0, 0 to infinity. Either one, I'm just going to use this. So we have psi star, which is just, psi is real. So it's e to the kappa absolute value of x times psi, which is b. And b could be a complex. It probably won't be, but I'll just keep a star on there. E to the kappa x dx from minus infinity to infinity. Okay, so that means 1 is equal to b squared. And then the integral, now I don't care about these absolute values anymore because they're squared, right? So I get e to the 2 kappa x, right? Oh, well, not, sorry, absolute value of x. Sorry, I do care. Sorry, I don't know what I was talking about. But since it's symmetric, like I don't need to do the whole thing. I can split it like I was talking about, right? So I can say, oh, well, it's going to be the same on this side that is on this side. So I can be like, well, this is probably going to be 2 times the integral. Sorry, I forgot my b squared. Let me get my b squared. 2 b squared times the integral of from 0 to infinity of e to the 2 kappa x, right? Because they're symmetric, right? It doesn't, if I do this side, I get the integral. It's just going to be the same on this side, so I can just multiply by 2. So that's the advantage of doing that absolute value. And so I'm going to let u equal 2 kappa x, du is 2 kappa dx. And so I get 2b squared over 2 kappa. And then I get the integral e to the 2 kappa. I'm skipping a couple steps from 0 to infinity. And this is the, wait, hold on. Right, so just a second. I think I've got something. Oh, yeah. Yeah, I'm sorry. I messed this up really bad. Sorry about this. When I go from here, I've got to use the right psi, which I didn't do. Okay. So to use the right psi, where if I'm splitting it, and I'm saying this is 2b squared integral 0 to infinity, I better use this psi, right? So e to the minus 2 kappa x, right, dx. Okay. So now we get, this is 2b squared over 2 kappa because of our substitution. And then it's just e to the minus 2 kappa x from 0 to infinity. The integral of e to the minus infinity is 0. So we get just the second term, e to the 0, which is 1. And I think I've lost a minus sign because I was being too quick. Sorry. There's a minus sign here. And so we get, this is going to be just b squared over kappa. And this has got to be 1. So that means b is equal to the square root of kappa. And of course, kappa, we already said, and I didn't write it down, right? I mean, I didn't keep it because we erased it. But if you recall, kappa is m square root of m alpha over h bar. And so we have b is the square root of m alpha over h bar. So now we finally have our psi. Okay. And we can write it as the absolute value for just for ease. Okay. We have square root of m alpha over h bar. We have e to the minus m alpha absolute value of x over h bar squared. Yeah, so hold on a second. I think I've lost the h bar. Why is there an h bar squared on there? Oh yeah, because it's kappa. Never mind. And then we also have e. So this is the bound state for the delta function potential. Now, first things to point out. Now, when we did both the TISE and the two bound states we've seen before, the two bound states we've seen before are the ISW, right, the infinite square well, and the quantum harmonic oscillator, right? We got infinitely many solutions for those. I remember this, like the psi, let me erase some stuff. And you guys okay with me erasing? Yeah. Just want to point some stuff out about this potential. Okay. All right, so this potential, let's look at like the infinite square well. That had psi, it had infinitely many psis that look like this. Right? And it had E. Right? And the general solution was this linear combination of all those things. And then e to the minus I e n t over h bar. I'm not going to fill in en because it's too much stuff to put into exponential. Fine. Well, for the quantum harmonic oscillator, we had the psi n's of x were these Hermite polynomials, right? Which I'm not going to write down because they're all different for every single n, but there's infinitely many of them. And then En, if I remember correctly, was h bar omega n plus a half. So infinitely many energies as well. And of course, the usual psi of x and t. like we always have, is just this, and actually it goes from 0 in this case, Cn, the psi n's, e to the minus I En T over H bar. But there's infinitely many of each of these solutions, right? That's what we came up with. But here, in this particular solution, and these were the bounds, these are bound state, right? Bound. Okay, this bound state here only has one state, right? There's no n's in there. This is the mass, right? M, right? It's a mass. Alpha is something given to us. It only has one energy and one state. Okay, so its general state, psi of x and t, is literally just psi e to the minus, m alpha squared over 2 bar, I t over h bar. Right, so this is e to the I, e to the minus I, e t over h bar, right? So it only has one energy and one state. So you can't make a sum out of it, right? Because it's only got one. So let me show you a little simulation. Just a second, I'm going to get up because I closed everything because previous class, this thing was being really slow. So.
Are you on video?
Yep.
Okay. Yeah,
Okay, guys, sorry. I got to share my screen just a second. Okay, can you see the little simulation? Okay, so we saw this before when we were just looking at the ISW. So like, for instance, we just make this really tall. You can see, there's different energy levels, right? This purple thing is the potential energy, right? Potential energy 0 in the well and very high outside the well. We can't really make it infinite in this simulation, but if you make it really high, it's going to be approximately okay. And you can see there's different energy levels, right, in this well. Okay, so if we want to make it really like a delta function potential, we should put this whole thing down to here and then pull. Oh, I just blew it. Sorry, let me configure the potential as well. So we're gonna, let me just figure out if I can make this, pull it all the way down. I'm gonna make it negative, and I'm gonna pull the height down to 0 here. And I can't really make it much farther down, but I can certainly make it thin, right? Like a delta function. And notice when I make it really thin, like right now it's at 0.2 nanometers, then I only get one energy state. And it kind of, sort of looks like our, you know, if you did psi squared, right? Psi squared would be e to the you know, minus kappa on this side, and e to the kappa x, and e to the minus e to the minus kappa x basically on this side as well, right? So you have this kind of like what we drew on the board, but you only have one energy, right? Because the well is really, really thin. And it seems like the fact that it's not, this is not infinitely far down doesn't matter that much. It's probably roughly close, right? This simulation is actually solving the TISE. So when you put in for the particular potential, it solves it for you and finds the energies and everything. So this is not quite the same because you can see the shape isn't quite right of psi squared, because we expect psi squared to be like, you know, e to the minus kappa x. So it's not quite like a dying exponential, kind of looks a little different to me than that. But pretty close, given that it's that symmetric about zero like we expect, and it's only got one energy. Does that make sense? So that's what that looks like. All right. So let's just keep going, because the next thing we're going to do, I'm going to stop showing this and show you, just let me stop here. All right. And then we're going to go and do the scattering states for this potential. So this is the first potential we've seen, including the free particle, where you could have both bound states, which we just saw for, and in fact there's only one, or scattering states. So if you look up here in our, you know, up here, right, where we're talking about what case we're in, we were looking at case 2. Here's the potential, right, going all the way to infinity. And we said we're looking for case 2 when it's bound. And for case 1, we haven't looked at yet. So we said, hey, let's look for E total less than 0. And that's what we did, right? And we haven't looked at E total greater than 0, which would be the scattering states. And that's what we're going to do next. So this potential, you could have either, depending on E, whether it's above 0 or below 0, you can have either scattering or bound states. Okay, so let me do some more. I'm going to actually get a new layer. No, that's not my new layer. I don't know why I put it way up there, but anyway. Okay, sorry, hold on. Okay, so let's look at scattering states. So that would be E total greater than 0, right? Okay. Let me just get my notes for that. I gotta find them. Thought I had this out, but apparently not. Okay, scattering states. So we're going to do pretty much the same thing we did last time. We're going to solve for on the right and then solve for on the left. Okay? And the TISE for both is the same, like we said before, right? So for x less than 0, TISE is minus h bar squared over 2m d squared psi dx squared is equal to e psi. X potential 0. And then for x greater than 0, so this is the left and the right, it's the same thing. Okay, fine. So let's rewrite this. We're gonna solve for on the left first, I think. Yeah, left. So we'll solve for left. And so we'll go minus h bar squared over 2m d squared psi dx squared, and then equals e psi. And I'm gonna pull all this stuff over like I always do. And so I'm gonna say this is d squared psi dx squared is equal to minus 2me over h bar squared psi. Now, e is greater than 0 here, right? So I'm going to keep the minus sign out of my definition of my constant. So I'm going to call this k, not kappa, not kappa, k squared. So different from kappa, right? K squared psi, where k is equal to the square root of 2me over h bar, just like before, but remember e is greater than 0 here, so I don't, right, this is going to be real, k is real. So was kappa, but it had a minus sign because e was less than 0. But I kept the minus sign out here. Okay. Again, always, if you have what's called the homogeneous differential equation like this, where there's always size or derivatives of size, you start with an exponential. So again, we're going to say let psi of x equal e to the lambda x, and of course d squared psi dx squared is just going to be lambda squared e to the lambda x. Okay, so let's plug that in. So we're going to have lambda squared e to the lambda x here, and then here we have equal minus k squared e to the lambda x. Okay, those are going to cancel out, and again I get something like lambda is equal to plus or minus I k, right? Because the minus sign gives me the I, and I get ik. Okay, so these are now imaginary solutions, right? So I can write down my general solution for psi left. This is all psi left. Psi left is of x is some constant times e to the plus I kx plus some other constant times e to the minus I kx. Now, we usually, when we have imaginary solutions like this, we write in terms of sines and cosines, which are always free to do. Here, it's just more convenient not to. As we saw, it was also more convenient not to in the free particle case. Okay, so we can't really do anything with this because neither of these things blow up at x equal minus infinity. Remember, this is the left, right? Like, they don't because they're oscillatory, right? So even if you put a minus infinity, and if you put a minus infinity here, you get e to the plus ik infinity. That's just an oscillated, right? These are just sines and cosines. It's like, what's the sine of infinity? Well, right, it wraps around infinitely many times, right? Like goes around 2 pi over many times. So, right, so the argument does inside the sine. Sine of infinity is just some finite thing. It's whatever the sine is doing at that point, right? It's not, it doesn't blow up, nothing happens. So we really can't get rid of either one of these because it's blowing up arguments like we did last time. That's a bummer. Let's do psi right. So psi right, again, we have exactly the same equation for psi right. I'll write it down again just to be clear. So on the right, we have d squared psi right dx squared is equal to minus k squared psi right. And again, we're going to go, let's do psi right as an exponential e to the gamma x. And then we're plugging in, we get gamma squared e to the gamma x is equal to minus k squared e to the gamma x, and cancel. And this gives us gamma, again, plus or minus I k. Okay, so again, now we have psi right. Psi right looks like this. Psi right of x looks just like psi left. Different constants. F e to the I k x plus g e to the minus I k x. So far, we're not getting anywhere by getting rid of any of our constants, these guys. We're trying to figure out what they are. So again, we can't even use blow-up arguments to get rid of anything. Because if you put positive infinity, because that's on the right, in here, let's say, you just get the sines and cosines of infinity, which are totally finite and fine. So I really can't get rid of anything. Okay, so we're kind of stuck with that. Now, we can use continuity. So remember, we have our first boundary conditions, continuity of psi of x everywhere. Okay, so that at least gets us somewhere. So that's at x equals 0, right? Because you've got the left and the right, they got to match at x equals 0. Okay, so at x equals 0, at least you can sort of match these and you can be like, all right, psi left, I don't want to take up all that space, sorry. Over here. Psi left at 0 better also be psi right at 0, right? Same thing. So at 0, we get a, because this is e to the 0 is 1, e to the 0 is 1. You get a plus b. And over here, you just get f plus g. So you don't really get a whole lot, but you get something. Okay? Not the most helpful of equations. And we can go through that whole rigmarole that we went through before, remember, for the second boundary condition? So the second boundary condition was continuity of d psi dx everywhere except where b is infinity. And we did that whole thing where we integrated over the discontinuity and all that. You can do exactly that, like exactly that. I'm not going to bore you with all that algebra. It's in your book, so I would, if you're like, I don't know how I would do that, go through and look. But basically, you get the exact sort of a very, very, very similar thing. I'll write it all down. So after doing all that work, you get I, K, F minus G minus A plus B is equal to, and this is from boundary condition. This is boundary condition 1. And this is from boundary condition 2. You get all of that and is equal to minus 2m alpha over h bar squared a plus b. This is not looking great, right? It's not looking great. I'm going to have to finish this next time, but we are actually having our presentations on next time, so we'll have to finish this on Friday. Okay? And then I think next week we'll start doing just problems. Okay? And I'll have your extra credit problems done by tonight. I'll put them on Moodle. Sound good?
Sounds good.
All right, well, we'll see some of you in MATLAB. Bye, guys.